Welcome to Advanced Reverse Engineering. There's homework. The homework is to disassemble some code using Python and Capstone, just so that you know the basics of how all this works. Hopefully you found this to be pretty easy. Open the file, find the text section, and disassemble all the code. Be sure that you produce the correct address over here. Remember that when you go into it, you're getting an array of bytes. An array of bytes doesn't know its address, so you need to provide the correct address to that method so that as it iterates through it and constructs instruction objects, it puts the correct address in each one of those objects. Should be pretty straightforward. Watch for exceptions, watch for unusual conditions. I've given you a little debug.py that you can use or not use. It's up to you. And some hints. I like doing things at the IPython prompt. Interactive Python's a pretty good way of doing things. It has a good history feature to it. Be sure and be aware of and use f-strings to make your life much easier. And there were some imports, etc. So let's talk about program analysis. So program analysis techniques really come in two basic categories. And this is kind of a weak categorization. If you want to analyze a program, you're going to end up having to do both of these things. But we tend to think of analysis techniques as falling into the control flow analysis bucket, where we ask, what instructions are going to execute in what order are they going to execute? And the data flow analysis, where we say, where is the data going within the program? How is it moving through the program as it's collected or it's processed and generated? And both of these represent a model of the computation, right? Control flow analysis is a model of how control flows through the program. Data flow is a model of how data flows through the program. And neither one is the program itself. And because of that, and because of interactions with themselves and their context and the environment the program runs in, you can be wrong. So you have to keep that in mind as you do these kinds of analysis. Some things we would think of as control flow analysis are code discovery, figuring out the execution order of a program, and determining whether or not a piece of the code is ever executed. That's a reachability problem. Some things we tend to think of as data flow are which values are relevant at a given point. That's the liveness question. What's the result of this computation? We can get that by tracing or by doing symbolic execution. And what parts of the program do I need to understand if I'm going to solve this problem? And that's program slicing. Now, doing any of these requires doing a little bit of both. So, this categorization, as I said, is weak at best. Analysis is hard. So, any sort of analysis other than purely syntactic analysis is generally undecidable, right? It's not purely syntactic, it's semantic. And if it's a non-trivial semantic question, it's probably in general undecidable. Doesn't mean you can't decide it for a particular program. It just means that you can't write a procedure, a finite procedure that will decide it for all programs. Now, the trick is we are presented with binary files, which are just buckets of bytes in our case an ELF container, and that's the syntax. That is the syntax. Source code is not our syntax. Assembly isn't really our syntax. Our syntax is just the raw bytes. So if you ask me a question about the raw bytes, like how many are there and is FE one of the bytes, I can answer those questions. They're decidable. But asking other questions can be really hard. Okay? So if we limit ourselves to static finite programs which don't have external references, you're probably in a world with decidable programs. But most programs reach out into the network to get data, or they modify something along the way. There's lots of things that happen that tend to make these things make analysis of them much harder. So we're going to discuss live variable analysis, static single assignment, symbolic execution with trace tables, and slicing, although not all today. And these techniques are well established for source code, but they can be applied to disassembly, and we're going to do that here. These are fundamental techniques for program analysis. You need to be sure that you understand them. Live variable analysis. So what makes a variable live? Well, a variable is live if I need to know what its contents are in order to understand what's going to happen next in the program. Okay. So here we say a variable is live at a particular point in the program if and only if its value at that point may be used to determine the future behavior of the program. What is the future behavior of the program? Well, it might be a control flow decision, or it might be an output decision. Okay. This means you need to know the future uses of the variable. It's helpful to have a structured program here if you want to do that. This analysis is used for things like register allocation when you compile programs, where we have lots of variables but only a few registers, and we want to figure out if many different variables can share a register, because maybe only one of them is live, meaning I have to know it at any given time. Now, this question is about program behavior. It's asking whether or not I need to know the value of a variable in order to know what's going to happen. That should tip you off that it's probably in general undecidable. And yes, live variable analysis is in general undecidable. So ask yourself, do I need to know the value of this variable at this point in the code? If you answer yes, the variable's live. If you answer no, it's not live, or maybe it's dead. And it's often better, if you're not sure, to say yes, because then maybe you have some information you're keeping around that you don't need, but you're not throwing away information that you do need. So there's two basic types. We talk about things being semantically live and syntactically live. A semantically live variable, v at some point p in a program, is live if there is an execution that starts at that point p, whose behavior can be changed in an externally visible way by changing the value of v. A lot going on in that definition. Externally visible, meaning it has some effect that we can observe. If it doesn't have an effect we can observe, then it's basically meaningless. Right? If it doesn't make the program run longer or generate different output, then I don't know how to make the argument that it's live. Okay? But it is changing the externally visible behavior of the program, right? So it's semantic. We can contrast that with the idea of being syntactically live. A variable v is syntactically live at some point in the program p if there's a path from p to the end of the flow graph, to exit, where the value of v at point p is read. That doesn't mean it's read at point p. That means the value that v holds at point p is eventually, somewhere later on along that path, read. Then we say it's syntactically live. Semantic liveness is in general undecidable. Syntactic liveness is generally decidable. I'm hedging a bit because there is a distance between bytes in a file and disassembly and determining that something is or is not read. And that can introduce some undecidability. So in general, we think of semantic liveness as undecidable. In general, we think of syntactic liveness as decidable. That's harder in our case. It may be easier in high-level programming languages, but it's certainly harder in our case. But that's in general a good way to think about things. If I can treat syntactic liveness as a proxy for semantic liveness, maybe I can get pretty far. So an interesting question here is it possible to be semantically live and not syntactically live? You're semantically live, you influence the program in some way, but your value is never read. See, that seems a little bit out there. But the opposite is possible, to have your value read but never influence the program. Sure, that's entirely possible. Right? I could move your value from one register to another. It's technically read, but if those registers aren't live, it doesn't matter. All right, enough of that. Let's think about syntactic versus semantic liveness. And let's take a look at this little piece of code over here on the right. And this code is Rust code. So if you haven't seen Rust code before, here's some Rust code for you to have a look at. We note that we don't make any claims about decidability. We just want to know if it's semantically live, and if it is it also syntactically live? Now, it's certainly the case that if I have a large set of things, and that set is, its membership is undecidable, right? The set of Turing machines that always halt, okay, that membership is undecidable. It may be the case that a subset of that is decidable. And so, in this case, that's what we have. We have the idea that syntactically live is or semantically live is a big set that may include lots and lots and lots of stuff. But syntactically live may itself be decidable. Sorry, I'm doing a bad job of explaining this, but you get the idea, I think. Over here on the right, we've tried to build our little Rust program, and you can see Rust has done the analysis to let us know that we do in fact have a variable that is not live, and that variable is y. Y is not live. And if you look up here, you'll see that we add 1 to y, we return y. It looks like it's live, but then up here we see the error. We've assigned x and y to x and x, and so the y that came in is never used. So let's talk about an algorithm to do liveness. Here's some code on the right, simple C code. And the question is, what variables are live in this function? And how do we count it? What does it mean to say a variable is live at a given line? So, for example, the line c equals 17, right? The prior value of c, before this line executes, is overwritten. And a new value is assigned. So we typically don't, it's sort of meaningless to say, is C live or not at this line? What does that mean? So the points we can consider are typically the point prior to execution of this line and the point immediately after execution of this line completes and before anything else executes. Those are the 2 points where we think we have defined values, right? Prior to the line and immediately after the line. Okay, so given that, we can begin to do some analysis of this little piece of code. So we know C is live just prior to line 9. Why do we know that? Because we're going to return it. And we're going to assume that returning it means that it's significant and someone's going to do something based on it. So we'll say that yes, we're returning it here. Return value of this little subprogram is C. So immediately prior to this return statement executing, C is certainly live. Okay. So we move back and we find other variables in here. And in particular, we find A and B up here. These are auto variables. They're created on the stack. You can see up at the top where they're created in A and B. We set A equal to 0. And so if we move backward from returning C and we look at let's pick on line 7, we see that the value that's in A immediately prior to this line is overwritten with the value B times 2. So prior to this line, whatever value was in A is not live. Okay? After this line, whatever value is in A is definitely live because we are going to use it to make a control flow decision. So we can continue to work backwards like this. So here's line 7. And let's think about what we did. We said, well, we overwrite A, so it's no longer live. But after this, it is. So what we did was, we said, well, A is an L value. So we're gonna remove it from the set of things that are live prior to this line. So suppose we have a set after this line. We know A is live after it because we checked A in the predicate. So A is live here. But it's an L value in this line. It's overwritten, which means it's not live here. So we'll take things that are L values out of the set of live values. Well, if we take something out, maybe we have to put something back in. Well, we know that we depend on B. B is read here. B is used here. B is used to determine what A is going to be. So certainly, prior to this line, B is live. So we start over here with after the line with the set of A as the only live variable. We consider this line, we remove A because it's an L value, and then we add all the R values. There's only one, it's B. So now our set of live variables prior to this line is just B. And we can keep working our way back through in this manner. We can move back to this prior line. We see that since B is live, and we do care about C, so I forgot C is also live. So C is live. C and B are live prior to this. We write to C, so we take C out of the set, and we put the things it depends on in the set, and it depends on the prior value of C and B, so C and B go back in the set and there's no change. Then we can work our way back to line 5, and at line 5, with C and B live after it, we find out that B is overwritten, so B comes out of the set, and because A is an R value, it goes in the set, so now prior to this it's A and C. There we go. So we wind up with this little set of live variables, and we'll talk about prior to lines, right? We're always going to talk about prior to lines or after lines. We need to be consistent. And so we'll talk about prior to lines. And so based on analysis, prior to 7, B and C are live. Prior to 6, B and C are live. And then prior to 5, A and C are live. Another way that's meaningful to think about it is we could draw the control flow graph of this program, and we could talk about edges. So let's think about that for just a minute. There's an edge that goes from line 3 to line 5, right? Because we start here, and the next thing we do is line 5. There's certainly one from 5 to 6, certainly one from 6 to 7, and then there's an edge from 7 to 9, but also from 7 back up to 5. So we have a branch here, and we can summarize what variables are live or not live on each one of the branches. We wind up with these sets that look like this. Where is A live? Well, it's live on 3 to 5, 7 to 8, and 8 to 5. 3 to 5 is here, 7 to 8 is here, and 8 to 5 is here. B is live on 5 to 6 here, and 6 to 7 here, and C is live everywhere. C is always live. It's passed in, and we return it, and we do stuff with it. So it's worth noting that A's live set, 3 to 5, 7 to 8, 8 to 5, and B's live set of 5 to 6 and 6 to 7 are disjoint. They don't share any edges, which means that A and B are never live at the same time. Never live at the same time. That means I could theoretically share a register or even share a variable. I don't need them both, right? And so I can, in fact, go ahead and replace B with A. Really, right? Because it doesn't matter. They're never live at the same time. So I take my original program, replace all the B's with A's, and I wind up with this new program which doesn't have B in it. I've eliminated a variable. So, does this help? Liveness analysis reduces the things that you have to think about and care about, because some things just don't matter. The values of some registers, the values of some parts of memory, maybe the stuff on the stack, those things just don't matter because they're not live. That's super useful in assembly. We have so much stuff that you have to think about. And it's a fundamental technique for doing data flow analysis. All right. Let's talk about static single assignment. So here's some code, a little piece of code that comes out of a library called ImageRank. And let's see what it does. It references RDI here, the value of RDI, but we haven't modified it prior to this, and this is the entry of the function. This indicates to us that the value of RDI is being read here, never set. This must be an argument to the function. And by the calling convention, we would expect it to be. RDI is the first argument to the function. If we look down through here, we'll see that RSI is also mentioned. Perhaps it's an input. We don't know yet. We'll do some analysis to figure that out. But certainly RDI is an input. Once we have RDI, we put it in REX. We then change RDI, and then we put the changed RDI into RCX, and so on. So a part of the original input variable, a part of the original argument to this function is in RCX, and part of it is in RAX. It's getting sort of spread out. It's getting harder to see where a particular variable lives. Well, RAX goes back into RDI. Okay, we put 1 in RAX, so RAX no longer holds the input argument. It's back in RDI. And then we reference RSI. Now we're reading RSI. We've never set it or mentioned it previously. So the only place its value could have come from was the entry of the program, so it must be a second argument to the program. And we're putting it in RX. So up here, RX held the first argument. Down here, it holds the second. So pretty soon, you can see where we're going. It's holding all sorts of different stuff along the way. Here, I pushed it. After shifting it, here I pop it. There's lots of stuff going on. This is sort of chaos. A register doesn't have a particular meaning or a particular use. It's just being used as it's convenient to do so. And the values it's holding are transient, and I can't necessarily connect them to the semantics of the top level program, or to any semantics other than the whatever is expedient at that particular line of code. So this gets complicated. It'd be great if things were assigned once and never changed, because then we could talk about what they were. We could do stuff with them. We could do math with them. We could say what they mean, right? If they were assigned once and never changed. If they were assigned and then their value was static. Static single assignment is what that is. So here's some code over here. 3 little statements. X gets Y plus Z, A gets X, and then Y gets X plus A. And we could probably figure that out by looking at it, but there is a technique that will help us, and that's to convert it to static single assignment form. The way we do that is we start out and we say the initial value of X, Y, and Z is X sub 0, Y sub 0, Z sub 0. So if that's the initial value, and this is the first line of code that runs, this is y0 plus z0. And now we increment that subscript and we say this is x sub 1. So x sub 1 is equal to y0 plus z0. And every time we assign a new value, we'll bump the subscript. So this is, if this is x sub 1 here, it must be x sub 1 here, and this must be a sub 1. We didn't modify x, so this must also be x sub 1. This would be a sub 1, and this is a new y value, so it's y sub 1. And we wind up with the expressions we have over here. This was particularly easy because nothing really gets overwritten very much, which is good. We want it to be simple. If we work through this, we'll see that we can do back substitution. y1 is x1 plus a1. x1 is y0 plus z0. a1 is x1. Those don't change, but this one is now y0 plus z0. And I wind up with 2y sub 0 plus 2z sub 0. And so this line of code down here basically tells me what's going on. I don't need x. I don't care about the initial value of x. And you can see that now, right? The initial value of x, whatever it was, is immediately overwritten. So x is not live prior to this line, but y and z are. And there you have it. So let's do this with a piece of code that you've seen before. This is a chunk of code out of the example I gave you before, with all of the different arguments that go to the function, one of which was on the stack. And it's a little piece of code that we can apply this to. And at the time, I in fact did this and used it to figure out the values. So here we say we want to move the value that's in EDI into EBX. An easy way to say that is EBX sub 1 gets EDI sub 0. And here we divide. So now we can break this xmm0 apart. xmm0 sub 1 is xmm0 sub 0 divided by xmm1 sub 0. And we play the same game for the other ones. And then if we back substitute to figure out what's in RCX here at the end, we find out that RCX is RCX0 plus R9 sub 3, which turns into R9 sub 2 plus R8 sub 0, which turns into R9 sub 1 plus RSI sub 0 plus R8 sub 0, etc. until we wind up with this expression at the bottom. In the original program, this was a sum of all of these 64-bit integers, and that's a way to figure this out. Well, that was straight line code. What happens when you have memory involved? Well, if it's just a couple memory addresses, maybe we can keep track of them. But it's probably more sensible most of the time to just say, you know what, there's memory. I'm going to call it M. And if it changes, I'll update M's subscript. And there you go. And we'll see that at work a little bit later on. What about branching? Branching is a problem. The code over at right contains some branches. It has a JE, or jump if equal, and a JNE, or jump if not equal. And those branches are going to change the control flow. So, why is that a problem? Well, first let's clean the code up a bit. This code has a return here and a return here. They go back to the same place, but it's weird to have two of them. There's a NOP here, a no-op, and there's a no-op up here. Why are there no-ops? Well, the no-ops are in there so that the targets of branches are aligned on a 16-byte boundary, right? So JE20, that takes us down here. Return. 20 is 2 times 16 in hex. And down here we have a JNE 10, which takes us back up here. 10 is 16. So we want those aligned. And to make them aligned, we add these no-ops so that we fill in the gaps and they end up aligned. That's also why we have two returns. Down here we flow straight through and return. Easy, fast, and simple. But because we want the return to be the target of this branch, we actually create one that's here at 20, which is a nice 16 aligned location. but then we need this NOP to fill in the bytes. So that's why we ended up with 2 returns. We don't need all this. We can simplify the code, and let's do that. Throw away the NOPs, throw away the extra return, and we wind up with the code you see right here. Simpler, pretty easy to look at. So we can do a number of things with this piece of code here. We could build a flow graph that would help us understand how control flow works in this little piece of code. We could convert it to static single assignment. That would be super helpful. We could try to do that. The interesting thing about trying to do that is, so when we do a static single assignment, I want to assign a subscript here. And I want to know what this value is. Well, it could be the value of RDI that comes from up here, right? Because I come here, I flow through this branch and wind up here. And so this value of RDI down here at address 10 might be the value of RDI originating up here at address 6. But you'll notice that I do in fact change RDI here at offset 12, and then I branch back around. So the value here could also be the value of RDI originating at address 12, and I don't know which it is. So if I want to do static single assignment, I have to figure out how to handle that problem. So first, let's make a flow graph, because this will make our problem immediately evident. You've seen me create these little circles on flow graphs where things come together. These are merge points. There's one here and there's one here, and it's nice to sort of call them out and see them explicitly. If I just draw arrows to boxes, you wouldn't necessarily see them, but by making them into circles and calling them out, you can see that flow does something here. The assignments of values to variables or to registers at 9 flows on to 10, but also whatever we have at 19 also flows on to 10. And I have to figure out how to merge those and how to reconcile them. Same thing at the end, right? The value of a register that ends up at 1B might have come to us from up here, from 9, or it might have come to us from 19, and we don't know. As an aside, this is a proper program. There's a single entry over here, a single exit over here, and there's no unreachable or trap code. And in addition, it's a nicely structured program. Here inside we have a sequence 10, 12, 16. That sequence is buried inside a do while loop, right? Do 10, 12, 16 while 19 is true. That do while loop is buried inside the else part of an if then else, right? If 9 is true, then we go on to 1B, else we do that loop and then go on to 1B. And then the entire thing is embedded in a larger sequence. So it's a structured program as well. We can simplify it. So if you go back one, you'll see that we had a little sequence of 10, 12, 16. Over here we had a little sequence of 4 and 6. We can just combine those. And so we now have this much simpler little flow chart, which only has a handful of nodes in it. So you'll see some flashing arrows there. Those flashing arrows are calling out the merge points, the things we've been talking about as being potentially problematic. The way we're going to deal with the merge points is we're going to create something called a phi function. These are hypothetical functions that will tell us which value to use. If RDI is mentioned in the body of the loop here, which we know that it is, do I mean the value that came from 9, or do I mean the value that came from 19 and came around the loop? Well, the phi function will tell me. It will just magically inform me of which one to use. I won't define the phi function. I won't write it down anywhere. I'll just use it. And you can see that happening up here at the top. So up here at 10, I say, well, EAX could be the EAX coming to us from line 9, right up here, or it could be the EAX coming to us from line 19, which is down here. And you'll see that 9 is a branch and 19 is a branch. So that's the immediately prior node that reaches this line. Same thing for RDI. Okay, so here I have these little phi functions that choose which one it should be. How do they choose? I don't know. Magic, quantum methods, who knows? I do the same thing at the end. What am I returning? I'm returning EAX, right? That's what the return value is in a well-behaved function conforming to the AMD64 calling convention. And so where does EX come to me from? Well, it could be the value flows down here from 19 and then here, or it could be I jump down here from line 9 from up here. Either one, I don't know which one, so I invent a phi function to do that, to bottle up that choice for me. Great, so now I have this new modified program. I've cleaned it up a bit from when we first saw it. I've added some phi functions to it. And now I want to walk through and try to generate the static single assignment representation. I'm going to make one change. Instead of, we can still have everything be 0 up here, but I'm going to subscript with the address. It's just convenient to do so. So when I say XOR EAX with itself, that tells me that after the instruction at address 4 completes, EAX sub 4 is 0. So this tells me something about this. I don't have an EAX sub 3 or 2 or 1, so don't be confused. This just tells me that EAX sub 4 is going to be 0. We can walk forward, and here we do a test. We test RDI against itself. So what RDI? Well, RDI sub 0 that came into the program. And why are we doing this? Well, we're doing this because it sets flags, and we could keep track of all the flags, but really we happen to know we only care about one, and that's the 0 flag. So we would say 0 flag sub 6, because it's address 6, is equal to RDI sub 0 equal to 0. So this is a little tricky. Let's be sure we understand things here. The 0 flag is true when it's equal to 0 and false when it's not. When the 0 flag is true, it's set. Its value is 1. When it's false, it's clear its value is 0, right? So if RDI is equal to 0, we're going to set the 0 flag. That can make sense from the point of view of like the C programming language, where I tend to think of a non-zero value as being true. If you think about that here, you'll do the thing. You'll do fine. So now the next thing is this jump if equal. Well, that doesn't modify anything. So you know what? I'm going to skip right over it. But now I have this EAX gets this phi function. Well, EAX from 9, I know what that is. The EAX that would be here is EAX sub 4, right? Because that's the only time I've set it. And so I can plug that in here. It's EAX sub 4. But what about EAX from 19? Well, that I just don't know. I don't know. So I'll leave it with a question mark. This is going to be EAX 10. That's what I'm setting here, because it's at address 10. I do the same thing for RDI. And so I know one of them, RDI sub 0. I don't know the other one, but I know this is going to be RDI sub 10. Now I'm going to add EAX and the contents of memory at address RDI. Aha! Now we have that memory problem I mentioned to you before. How are we going to deal with that? Just like I described. We're going to have an M sub 0. That's the memory state as it comes to us. And we're going to reference it, we're going to index it with RDI sub 10, because that's the value of RDI at this location. We're going to add that to EAX sub 10, and the result will be EAX sub 11. Now wait, Stacy, you might say. I thought that was an address. This line didn't have address 11. It has address 10. Yes, I'm taking some liberties with my annotation. What you might do if you're trying to program this on a computer instead, you might just say, well, it's 10, now it's 10.1 or 10.2. Okay. But here, it's convenient to just use 11 because we don't actually have to use address 11. So moving on, we go to the next one, which is that move instruction below it, and it references memory as well. And so again, memory hasn't been written to or changed, so it's M sub 0. And it's RDI 10 plus 8, and we're going to put that into RDI 12 because 12 is the address. Then we do a test. Remember last time we did a test, we said, well, the 0 flag is going to be true if this thing is 0. We do the same thing here. So now we have ZF16, which is true if RDI 12 is 0. And then we do that branch. Now, if you take a quick look, you'll see that right here, we're about to take the branch at 19. We'll be able to fill these two things in. What is EX here going to be? Well, it's going to be the EAX when we take the branch, which would be EAX 11. What is RDI going to be? It's going to be the RDI when we take the branch, which is RDI 12. So let's go ahead and take the branch. And we see, sure enough, it fills in with EX11 and RDI 12. The branch doesn't have any special semantics for it, so we just move right along. We have another phi function here, so we play the same game. The EX that comes to us from 19 is EAX11. The EX that comes to us from line 9, or from address 9 up here, is EX4. So we fill those in, and then we're done. And so now we've taken what we have over here, and we've converted it to a symbolic program that is in static single assignment form, and we can do back substitution with it. It gets a little tricky with the phi functions, but that's okay. You wind up with a little bit of recursion, and you can often resolve that and figure out what's happening. Let's talk about symbolic trace tables. Throwing lots of topics at you. Can we make it easier to figure out static single assignment? Well, there were a couple of problems that we had. We had to figure out the subscript. And you remember, first I was like, well, we'll just add one each time. And then it's like, well, I'll use the address, except in this one case where I'll cheat and not use the address. And then there were some conditions floating around, like whether something was less than 0, or equal, whether something was equal to 0. And, we didn't really keep track of those. So, and it may have not been clear to you how we were using that to figure out what the program is doing. Helping us do all that in a way that can be automated is where trace tables come in. The basic idea is build a table, rows and columns, with one column for each variable that we're tracking and one row for each program line, or in this case instruction, and a column for any conditions that we know to be true at that line. And so if multiple things are happening at a given line, we can just break that into multiple lines so that we can break things apart. For example, with the loop instruction, we're going to decrement a register. We're going to check to see if it's 0. There's many cases in assembly language where several things are happening, and we might need to break them up so we can analyze the program. So here's our piece of code again. You'll remember this. This is the one we had earlier where we figured out that A and B were never live at the same time, and we could replace one with the other. And let's ask the question, what does this actually do? So the way we're going to attack this problem is we're going to build a trace table for the body of the loop. So before I do that, let me stop for a minute and say, feel free to pause the video, take a look at this program, and try to answer what it does, just by some hard thinking. And if you've done that, we're ready to move on. So, we're going to build a trace table for this program. We're going to start again, like I said, by analyzing the body of the loop. It usually makes sense when you're doing this in an automated fashion to start in the inside and work your way out. If you're a person doing this, you can probably see ways to cheat and not have to do that. But again, programs aren't smart. They'll have to start somewhere and have to follow a procedure, and the best procedure is to begin in the middle and then work your way out, or begin at the most nested level and work your way out. So if we look at line 6 right here, C gets C plus B, right? We're going to want to say something like C at 6 is C at 5 plus B at 5. Make sense? And we're also going to say, well, B at 6 is B at 5. So we're going to keep track of things that way. We'll use subscripts to make the variables represent fixed values, so we have static single assignment, and we'll wrap it all up into this table to see if we can get somewhere with it. Here we go. So I've identified the body of the loop here. I've broken out these 3 statements. This is statement 1, 2, and 3, and they correspond to the rows of the table we have over here. You'll notice at the beginning of it, I've marked A as A sub 0, B is B sub 0, and C is C sub 0, and I just called the 3 lines of the body of the loop 1, 2, and 3. They were 5, 6, and 7 over here, but who cares? The numbers are arbitrary. So this line does not change A. So A sub 1, or A after line 1 completes, is identical to A after line 0 completed, or before line 1 ran. Same thing for C. But B changes. B sub 1, B after line 1 completes, is equal to A before the line started plus 1. Make sure it's all clear. A sub 1 is A sub 0, C sub 1 is C sub 0, B sub 1 is A sub 0 plus 1. We'll do the same thing for the next one. Should be easy to predict. B is mentioned, but it doesn't change, so we'll have B sub 2 equal B sub 1. A isn't even mentioned, so A sub 2 will be A sub 0. And C is mentioned, and so we'll wind up with C sub 2 is C sub 1 plus B sub 1, and there it is. That's exactly what we get. Down here at the bottom, we do the same thing again. So we wind up with A sub 3 is B sub 2 times 2, B sub 3 is B sub 2, and C sub 3 is C sub 2. Now we're writing a lot of stuff down. In reality, even if you were programming this, you wouldn't waste the memory on the ones that don't change anything. You would just go ahead and say, well, I know what those are doing, and you would omit them. But for right now, let's pull the ones out of the bottom of it. A3 is B2 times 2, right there. B3 is B2, right there. And C3 is C2, right there. And let's back substitute. So we'll move our way back. We'll substitute here. So B2 is B1. B2 is B1. C2 is C1 plus B1. And then one more step. B1 is A sub 0 plus 1. There it is again. And C1 is C0. B1 is A sub 0 plus 1, just like it was before. And there you have it. Let's do a little bit of additional work. Immediately prior to the loop, there's an initialization condition that we can take into account. And this is pretty normal. If your program is if you're analyzing the code, you may wind up with a ridiculously complex expression for the body of the loop, because the body of the loop is not taking into account context clues around the loop. It's just computing what the loop might do given any context. And so here we actually specify something about it. We constrain the function of the loop by saying initially A sub 0 is 0. Well, this A sub 0 is all over here. Let's substitute. When we do that, we find out that when the loop finishes, A sub 3 is 2, B sub 3 is 1, or when the body finishes, and C sub 3 is C sub 0 plus 1. So the first time through the loop, we started with A0, we go through the body of the loop just once, we set this to 2, this to 1, and we add 1 to C. And then we check the predicate to see if A is greater than 9. Is A greater than 9? No, it's not. A is 2. 2 is not greater than 9, so the loop will not run again. And so we will return that. The net effect of this whole piece of code here is to increment the value of C. You pass in 17, I return 18 after confusing you with all this math. So hopefully that's what you got when you stared at it really hard. But here we did it systematically using an approach that you could write code to do. So now let's talk about assembly for just a moment. We're going to do the same thing, but we're going to go back to the program we looked at earlier with all the phi functions, and we're going to work our way through it and see if we can put it into a trace table. So here we've done the same kind of thing we did before. We have instead of cheating and using 11, you see I've been a little more conscientious, and I've said, well, this is address 10, and this is 0.1 for this the phi function. Excuse me, stammering. 0.2 for the other phi function, and then down here is 1b for this one. But you see I've broken the phi function apart into the two pieces, ex from 9 and ex from 19, RDI from 9 and RDI from 19, and we'll see how that plays out. And then up here I'm doing the usual stuff. Here I've set EAX to 0, so I say EX4 gets 0. RDI doesn't change. The 0 flag is 1. Yeah, it is, isn't it? So I'd say ZF sub 4 is 1. No condition associated with this. The next one, same kind of thing. Next one, same kind of thing. You should be able to follow these through without me having to explain them all. So now we've split the phi function apart. First line deals with the first slot, and the second line with the second slot. And this lets us specify conditions for the path that leads there. So here's what that looks like. So here EAX gets EX from 9, so that's EX 10.1 is EX 9 because that's the value we're getting. RDI doesn't change, and the 0 flag is 0. Why? Because the condition that led us into this had it 0. We're coming in from 9, from right here. So right here we know something. Jump if equal, right? That means if we was 0, if the 0 flag was set, we'd be down at 1b, but we're not, so that means we must have had this 0 flag clear. It must have been 0, and we can deduce that, and we can capture that over here, and in fact we can capture that here as well. So now we know something about the state of the system and can capture it. Here we're coming from 19, and so let's ask ourselves, and we can get all these, but what about the 0 flag? So down at 19 we have jump not equal to 10. So this is the same as jump not 0. So it's jumping when the 0 flag is clear. So the 0 flag is 0 when we come that way. So sure enough, we capture that over here as well. We do the same thing for RDI from the two different paths. And we continue, and we can fill in the rest of the table this way. We have a few places where this is going to be 1, because again we took the branch to say that we were equal, like right up here at 9 we said, well, jump if equal, or jump if 0, and that takes us to 1b, so sure enough we'd say that this is 1, and we'd say it's 1 here as well. So there you go, we've now filled this whole table in. Many cells contain no change assignments, and I mentioned earlier we could discard those, and should, to save space. If we do that, we wind up with this much simpler table that just tells us where there are effective changes in values, and you'll see memory mentioned a few times in here. So back substitution won't solve that. We'll end up with recursive expressions, which indicate that we have a loop. The idea is we can do a combined structural analysis. Control flow was part of that. Data flow analysis, right? We did some data flow stuff to figure out what the program does. This is a short disassembly, and we'll see how to figure out what it's actually doing, what this thing is actually doing when we talk about memory shapes. But you see, we can go ahead and we can do back substitution now. I don't have slides for it, but you can do that yourself. We know the return value is going to be EAX. We know it's going to be one of these two values, and then you can substitute for these and work your way back through, right? EX is going to be EX9, and we look up here and find out what EX9 is. It's going to be EX19, and we look back and figure what EX19 is going to be. And you may say, well, EX9 and 19 aren't mentioned here. That's because we erased the cases where they were carried forward, right? So if I go back one and fill them in, there's EX19, it's EX16, 16 is 12, 12 is 10.3, 10.3 is this memory expression. So you could work your way back and find out what those were. And you'd wind up with a couple different cases. And as you substituted, you'd wind up with a case where you came back to, you started out with EX19, you substituted, and you wind up with EX19 again. And that would be the indication of a loop. And then the question is, what do you do about the loop? How do you eliminate the loop? And there's a ton of different ways to deal with loops. But something has to be hard, otherwise everything would be decidable, and we know it's not. So there's a piece of this that has to remain, in general, undecidable, and that's going to be where you see recursion. All right. So that's it.